Okay, so in this tutorial we are going to summarize the key points made by today in regard to the second law of motion and give you some practice examples. Part of it will be done on your own. We'll pause it and then I'll give you the answers, and then we'll address further questions in class. Okay, so the second law of motion is a central equation. It tells us what happens when you have force or forces acting on an object. It's an equation. It looks simple. It's actually fairly complicated, but we'll address that later. So if unbalanced force or forces act on an object, then it must. All right, that's in key. The unbalanced part is critical here. Accelerate at a rate proportional to the net force. In other words, A is proportional to F net mathematically, and inversely proportional to the object's mass, or put another way, inertia. Okay, so we know that A and M follow an inverse relationship, and here A and F follow a direct linear relationship. All right, so this can be summarized as we said in class: A equals F net over M, or it is commonly written as F net equals MA. Okay, I prefer the first because it tells us what A depends on, the net force and the mass. This second equation does not tell us what F net depends on. It's just mathematically equivalent to it. It turns out that this equation, A equals F net over M, even though it's ubiquitous in all physics classes, is actually a special case. It is not the most general form, but as an introduction, it's a good place to start. So it only holds if you have a constant mass. You might ask, well, what situation we wouldn't? A classic case would be rockets. When a rocket blasts off, it's ejecting mass at a very high rate. So this equation really doesn't hold. We have to generalize it. Okay, but we'll address that another time. Units, we talked about in class. All right, so if F equals MA, they have to be the same units as M times A. So that would be kilogram meters per second squared. And that has a name, a Newton, as we discussed. And that's given a symbol, capital N. Okay, so very simple example, and they'll get a little more complicated. Net force, that word net is really important here, acts on an object westward that's moving east, and what must happen to the block. Since there's an F net, it must accelerate, so let's calculate that acceleration. So the acceleration is simply F net over M. Okay, so I'm going to call west positive, what the heck. So we'll call it 20 newtons divided by 4 kilograms gives us 5 newtons per kilogram, which is the same as a meter per second. Oops. Meter per second squared. Okay, pretty straightforward. So note that our acceleration came out to be positive, meaning it's to the west. We'll see where that comes in later. All right, so when no more forces act on a block, what will happen to it? So we take away this 20 Newton force. Think carefully, think. Hopefully you didn't say it will come to a stop. All right, if we take away the net force, it will simply continue moving. The only reason it would stop is if there's a net force that would make it stop. Okay, now we can turn to kinematics. Pretty straightforward. How fast is it going to be going after 4 seconds? Well, how fast is the final velocity? This is a time. We now know the acceleration, so we can say final velocity is initial velocity plus AT. We're given initial velocity here. Now this is to the east, so that's a -3 plus 5 meters per second squared times 4 seconds. And so we got 20 plus a -3, which is 17 meters per second. So what I want you to note here is the net force was to the west, the initial motion was to the east, so what was the consequence? It slowed down. It's slowing down the entire time it feels that net force, and we can see by the fact that it went from a negative value to a positive value. So I take that back. It slowed down, came to a stop, and then started gaining speed in the other direction. All right, what direction is the block moving? Well, we came up with a positive value, so that is westward. And that's only because this time was long enough for it to turn around and stop. Conceptual questions. If the net force doubled, which of the following would double as well? circle all that apply. Okay, so take a second to ponder that, and I'm going to pause it here. All right, so hopefully you use the second law. We're talking about net force. We see that F net is equal to MA. So A definitely doubles. Notice that velocity does not show up in this equation at all, so we have no idea. So we can put IDK. We have no idea if the final speed is going to be double or triple, because that depends on how much time to force. How about inertia? M is inertia. Is that going to double? And the answer, hopefully you realize, is no. That the force does not affect mass. They're related in a way, but one does not affect the other. Okay. Instead, the inertia of the block doubles. How would the following change? And give as a proportion. All right. So how would the following final velocity change if we were accelerating twice the mass? Again, our equation is A equals F net over M, and I don't see anything about velocity in here. The best I could do is take this out and put in V minus V naught all over time. Okay, that's supposed to be a minus sign. I don't have any information about this, so we have no idea what this is going to be. Acceleration, okay, well that definitely ties in with the second law, as we know by now, and we see A and M are inversely proportional. So if I've got double the mass, I can basically say A is proportional to 1 over M. So I can say my new A prime is going to be 1/2 the original acceleration. Net force, does net force depend on mass or inertia? And the answer is no. These two are independent of one another, so there'd be zero change. All right, so that's really the second law in a nutshell. Before we get into more complicated problems, like we addressed later today with the force diagrams, let's look at some simple schematic type problems. Okay, so I will do one with you, and then I want you to try to rest on your own and see if you're doing it right. So what we're going to do is we're going to represent a body with some forces and given information about mass, and you're asked to figure out some things about it. Okay, so here I have a force that's acting upward of 10 newtons on a 2 kilogram mass, and I ask and up and right are positive and down and left are negative. So F net would be the sum of all the forces. There's only one force, so in this case it's very simple. It's positive 10. The acceleration then would be 10 newtons divided by 2 kilograms, which is 5 meters per second squared. Okay, so that's about as simple as it gets when it comes to a second law problem. What direction is the object moving? Well, we're not told anything about what the initial velocity is. We don't have any idea if it started from rest or if it was moving up or down, left or right. The point being, knowing the direction of force does not tell you any direction about the velocity. So again, we don't know. I can't emphasize that enough. What you do know is that the acceleration is upward because the net force is upward. All right, so try numbers 1, 2, 3, and 4 on your own. Give yourself, I don't know, maybe 5 minutes to try these. And then pause it right now and then unpause it, and we'll talk about what the answers are. All right, so let's go through these. In this one, we have 10 newtons up, 6 newtons down, so our net force would be 10 minus 6, or 4 newtons. And so the acceleration is pretty straightforward. 4 divided by 2, 2 meters per second squared. All right, what would happen if an additional 4 newtons down was added? Well, I'm going to put a 4 newton arrow down, and I add these all up. 10 plus negative 6 plus negative 4, and I get 0. Okay, so what would that mean? 0 net force means no change in motion, no acceleration. All right, so like I said, no acceleration, net force is 0, no change in motion, they all go together. What if there are 3 forces? Well, we just saw in the problem above. We have 4 to the right, 3 to the right, so that's 4 plus 3, 9 to the left, minus 9 gives us negative 2. The negative simply meaning where net force is to the left. The acceleration is negative 2 divided by 4, so negative 0.5 meters per second squared. Okay, so we're accelerating to the left. That doesn't mean we're moving to the left. It could be, we don't know. If the mass of the object were halved, by how much would the acceleration change? So once again, A is proportional to 1 over M. So our new a is going to be proportional to 1 over 1/2 the original m, which is nothing more than twice. So it's going to be twice the original acceleration. 1 divided by half being 2. Okay, let's continue on. Hopefully you're seeing these aren't too bad. All right, in this problem, we're given one of the forces unknown, but we're getting F net. So what I'm basically saying here is, since these two are in the same direction, I'm going to say F plus 6 equals, actually, I got to be careful about that. I know the answer conceptually, but I want to make sure we set it up correctly. The answer, the absolute value should be 15. Okay, 15 down. And basically what we're saying is, if down is negative, negative F minus 6 equals negative 21. So if we solve that correctly, we would get negative 15, which means that the magnitude is 15. 15 down is the same as, the 15 down is the same as negative 15. So the acceleration would be negative 15 divided by 3, which is negative 5 meters per second squared. And the negative just means it's going to be accelerating down. All right, if acceleration was 0, then what would be the magnitude and direction of F? Well, if I have 6 down, then I want 6 up. So it would be positive 6, and therefore F net would be 0, because F net of 0 goes with an acceleration of 0. And lastly, a proportions problem, once again, maybe just a little bit more difficult. So how do they compare? Well, we'll calculate. So the acceleration of this guy is the force on it divided by its mass. Okay, so I'm going to leave it like that. And for B, it's the force on it divided by the mass. They're not the same thing. So we can compute a ratio. So AA to AB would be 2F divided by M divided by F over 2M. That's a mess, so let's do copy, change, flip. So the F's cancel out, the M's cancel out, 2 times 2 is 4. So A has 4 times the acceleration of B. All right, you probably could have figured that conceptually, but it's important you be able to work it out mathematically. All right, so on the back are more homework problems. You don't have to do those tonight. I'll assign them to you tomorrow.